So what we talked about last time, let me just kind of walk us through this a little bit. We have been changing degrees to radians and radians to degrees. We just had a brief discussion of what we do when there's minutes or decimal portions of a degree, so hopefully we've got that straight. We did talk about the unit circle and how if you have a unit circle to look at, it might be helpful. But we also know that it's very doable since we know how to draw the triangles, that we could find sine, cosine, tangent, any of the values we would want for those reference angles, the special right triangles. For any quadrant, it would give us a tool if we didn't have a unit circle. So we walked through how to compute those. We also discussed how you would use your calculator to get reciprocal functions, either secant or cosecant or cotangent, because we don't have buttons for those, when we've been given an angle measure in radians. What's the one thing you got to make sure you double check before you would, and why is this not saying, hold on, audio options, computer audio connected. Okay, it's showing, we'll see. Normally it shows me that I'm talking and it's not saying that, so I don't know if it's recording audio or not. I apologize if we end up in short videos, but we'll give this a shot and see what's going on. So to make sure we don't mess up when we use the calculator, what is it you got to double check before you type this in? Radian. Exactly. Go to mode and you got to make sure that you are in radian mode, not degree mode, or you will not get the right answer. Now, the last thing we did in the last class is we discussed the difference between linear speed and angular speed, and we got some new formulas. Linear speed, think about it, that's when your unit is to the first power. So typically when we talk about speed, it's things like miles per hour or feet per second or something like that, all right? So that means I've got some distance I can measure. When we measure distance, the unit's only going to have a power of 1, and that would be over a period of time, how you traveled. So even with a circle, we can do that, because if you're just going around the outer edge of the circle, it's just a singular unit, whether it's, you know, inches. It could be radians if we want to use the unitless measure. That's an option. But then we talked about angular speed. Think about the hands on a clock. What do the hands on a clock do? They move around the clock face, don't they? In order to keep time accurately, does it have to travel at a constant speed? Absolutely. But think about the difference between the second hand and the minute hand. Is the speed that the angle is changing the same for those two hands? No, the second hand goes a whole lot faster, right? And then if you compared the angle, the speed of the angle changing on the minute hand to the hour hand, that's different too, isn't it? So you can measure angular speed. We have the symbol that is omega, the Greek letter omega for that formula, and we determined that that gave us some additional tools that we could use in finding linear speed. So the omega, or the angular speed, is always whatever the angle measure is divided by time, because you're looking at how many radians per whatever is it moving, and we want to keep that unitless so that when we're working in formulas, we're not having to have degrees. So if they gave us degrees, we want to change it to radians before we turn it into angular speed. But look at these options that we get when we're calculating linear speed. We found earlier that S was that arc length, right? The distance you've traveled around the circle. So if they give us that, all we have to do is divide it by time, and we've got B. But we also had a formula that told us that to find that arc length, it was radius times the angle, right? Angle theta. So we could substitute r times theta for s depending on what we've been given. And now, since we know that omega is theta divided by t, look at this. That theta divided by t is this part of the formula here. So that's why r times omega would also give us the linear speed. So we went through this part of this problem, ran out of time. We're going to wrap this up, and then we're going to move into section 3. So find the linear speed of p. Okay, and p is the point that's moving on the circle in inches per second. So if I'm looking for linear speed, which letter is that? Am I looking for v or am I looking for omega? That's v. Linear speed is v. And now I've got to decide, based on the information I have, which formula do I need for v? What do you guys think? He thinks radians times omega. Do y'all agree with that? Yes, no, what? What do you think? I think that's an awesome way to go, because look up here. They gave us the radius and they gave us omega. So we don't even have to use any pieces we found up here. We can actually use what we were given in the original problem. And our radius was 15 inches. And our omega was pi over 12 radians per second. And remember, radians is actually a unitless measure. When I finish with this, am I going to have the right unit, inches per second? What do you think? I am, because remember, radians is unitless, so I don't really have to count it. I'm going to have inches on top over seconds on bottom. So all I have to do is clean this thing up a little bit. What's that going to give me? 15 pi over 12, and that 15 and 12 has a common factor of 3, so I could reduce down a little bit. That would go 4 times, that would go 5 times, and I would get 5 pi over 4 inches per second. Make sense? I was going to say, if it stays that easy, life is good, is it not? All right. So let's see if we can do this one. We've got a belt that runs a pulley that has a radius of 5 inches, and it is traveling at a speed of 120 revolutions per minute. Now, what does it ask us to do? It says find the angular speed of the pulley in radians per second. Okay, angular speed is which formula? Good, that omega. So omega is going to equal, what am I supposed to do? What was my formula to find omega? Angle theta divided by time. And I wanted angle theta to be in radians. Now, have they given me an angle measure here? Not exactly. What did they tell me?
120 revolutions.
So that 120 revolutions per minute is not in radians, but maybe I can do one of those, why is the word escaping me? A unit conversion to get it into radians. That's what I'm wanting to say. So let's see what we have. If we start off with 120 revolutions per minute, and we want to get that into radians per second for our final answer. And we're going to multiply, or we're actually going to divide that by, and if it's okay with you, can I just extend the line like that? Because if it's revolutions per minute, it just means that revolutions is in the top of the fraction, minutes is in the bottom. Time is supposed to go on the bottom. And do I have a time here? Well, in a sense, I do, because it's 1 minute. Okay. Now, in order to figure this out, okay, I would need to convert this so that I end up with radians per second. Now, talk to me about revolutions. Revolution means how many times you do what?
1 full rotation.
Say again?
1 full rotation.
1 full rotation. So what I want to do is see if I can come up with 1 revolution would be the same as how many radians? What do we define 1 full rotation to be in radians? 2 pi. There you go. And that means my revolutions are going to cancel out. And if I stop here, I've got my answer in radians per minute. But I want it in radians per what? Per second. So in order to change minutes to seconds, that means I'm going to need minutes on top. So it's going to cancel out with this minute. And 1 minute is the same as how many seconds? 60. So now, if I multiply everything together, the only unit on top is radians and the only unit on bottom is seconds. I just got to figure out the number that goes with this. So I've got 60 on bottom, 120 on top. I know that's going to go in there 2 times. And that would mean my omega is how much? 4 pi radians per second. Okay, now think about that for a minute. If it's 4 pi radians per second, then that means each second this thing's spinning how fast? How many revolutions? 2. Yeah. So it's going around twice in 1 second. Okay? Now, find the linear speed of the belt in inches per second. Did I even have to use this on the first part for angular speed? But am I probably going to need it down here for linear speed? Yes, and I'm going to use what for my formula? I've got 3 options on how to find linear speed. What do you think we need? We could have V equals S over T, V equals R times theta over T, or V equals R times omega. What do you think would be the easiest one to use? I would use R times omega because we just found omega and they gave us the R. So my R is 5 inches and my omega was 4 pi radians per second. And my unit for my answer is supposed to be in inches per second. Isn't that what I'm going to end up having here when I multiply? Because radians is unitless, so it doesn't matter. I've got inches on top, seconds on bottom. So that ends up being what? If I multiply this together, I get 20 pi inches per second. And if we wanted to get an approximation for that, what would you do? Exactly. You want to take your calculator and you want to multiply 20 times the pi key in your calculator. So 20 times pi, that's that second rooftop, second exponent thing. So if I rounded this to the nearest inch, that would be about what? Looks like 63 inches per second. Is how fast that thing's spinning. Okay, so that wraps up section 6.2. Do we have any questions on that, or you guys okay? All right.
So does that mean if we lay that belt out that it's going to be 63 inches long?
Not that the belt is. What that means is that the belt will have traveled, you know, because it's pulling the thing. It will have traveled 63 inches in a second. It doesn't necessarily have to be that long.
Yeah, that's what I meant.
Yeah. If I measured off the distance of how far the belt moved, that's what it would tell me.
Which is the same as like if you were to roll out the pulley itself, how many inches it went around the pulley.
Yes, because remember this, we already figured out in 1 second the pulley was spinning 2 complete revolutions.
Mm-hmm.
So whenever we're looking at the linear speed, then in 1 second it's gone 63 inches. And you know, since the radius was 5 inches, I'm pretty sure we have gone around that belt. I mean, you know, we have traveled more than the distance of the belt because it's had to spin around further than that. All right. here's what I'm looking for. I want to show you guys something as we get ready to move into 6.3. We kind of looked at this before. Okay, let me see if I go to this. And okay, what I want to talk about, let's close that up, is those graphs again for sine and cosine and tangent. Now, I personally think this is kind of a cool site. So you may decide that you would like this link, and if so, I'll be happy to share it with you. But this gives you a quick visual. I want you to, first of all, look at this. See, as you're rotating through the unit circle, then what it's doing is graphing, and think of it as a coordinate plane, but it's continuing to move, bless you, through multiple quadrants here. I want you to see if you can figure out what this ratio appears to be. So check right here, when we're at 0, it was on the axis. There's high. What's this doing? 0, -1. What curve is this? Aha, which means it is sine. Perfect. And that's why it's a wave, all right? It continues on over and over, and that would be when you take it from the unit circle and you put it on an XY axis. That's why it looks like this, because we're using the X values here. What the actual ratio ends up being is the value for the Y. Okay, that's how we graphics. We're going to start talking about the graphing of this in a little bit. Now, I do want to show you this quickly. I just thought there were some cool things in here, and they actually have some practice things too that you can do. This is not the one I was looking for. Evidently not. So let me go back again, and that's probably what I wanted. Okay, so this would give us a visual of what the sine graph looks like if we were graphing it using radians for our X values, our degree measure. Well, instead of degrees, we're going to use radians. So I know one complete circle is 2 pi. That's one complete cycle for the sine graph. And again, if we know a hala, we're at axis at 0, we go up to a high, back to the axis, down to the low, and then to the axis to finish up. The difference with cosine is what? Yeah, you start high. You know, that's hala. So you've got high, axis, low, axis, high, and that gives us one complete cycle in 2 pi radians. Now, if you put them together, this is the part you got to make sure that you see visually, they're the same graph, right? It's just that there is a shifting over of, say, the sine. If you shift over pi over 2 radians, okay, that's what the cosine graph looks like. Or if we were talking about the cosine graph, then you could shift to the right, pi over 2 radians, and it would look like the sine graph. Here's your tangent function. And remember, we know there are some values that were undefined because we ended up with 0 in the denominator. And that's why you have these series of asymptotes, and then you get these curves that just repeat over and over and over. Now, these 3 are all functions, right? If you remember from algebra, if I'm looking at a graph, what's the quick way to test to see if I've got a function?
A line.
If it passes a vertical line test. And none of these fail a vertical line test. Even though this is squeezing closer and closer here and it almost looks vertical, it never gets vertical, right? It's always squeezing just a little bit closer. So all of these are functions. Now, somebody asked last week, I think, about those inverse graphs. You remember that? I'm kind of getting to this a little earlier than when we'll do homework on it. But I think it's helpful to see this. Let me, first of all, do you remember what an inverse function is. How do you get an inverse of a function? You switch the x and the y. Let me just kind of show you quickly. We talked about this in business calculus yesterday. So if I had a function like y equals x squared, all right, you guys know what that is. That's what?
Parabola.
That's a parabola. That's a quadratic equation. To get the inverse, you switch the x and the y. Right? But then you're supposed to rewrite the inverse so it would say y equals. Now that's where we end up with a little bit of a problem, because to get the y by itself, I've got to take the square root of both sides. And if I'm putting the square root sign in here, I got to remember that so let me stick this up here so you can see. That if I'm putting in the square root sign, I got to remember there's both a positive and a negative root, right? Because if I said, what number can you square to get 4, you better give me 2 answers. What's one of them? I would need -2 and I would need +2. If I only give one of the answers, I haven't given all of them. So if I'm asking what can you square to get this, you've got to make sure you tell me both the positive square root of x and the negative square root of x. So if we were to write this out in inverse form, it would look like that. Now, here's the problem. I'm going to put this on the graph. And since y equals x squared is a parabola that opens which way, up or down? Up. I'll plot just a couple of points here. Okay, I would get a parabola that looks something like this. That's my y equals x squared. And that's a function, right? But what happens if I try to plot this thing? It ends up being something that looks like, oops, sorry, ends up being something that looks like this. Now, is that a function? No, and so that's a problem. That's why in order for a function to have an inverse, the inverse needs to be a function as well. So this really is not a true inverse. What we do so that we end up with a function is usually we just take the positive square root, okay? And that's a function if we just do y equals the square root of x. But if we have both parts, it won't pass the vertical line test, okay? Now, that's not, if I'm only using the positive, that's not an inverse of this. It's just another function. But for a real inverse to exist, the inverse has to also be a function. So in other words, I need to make sure that I'm using a function that's one-to-one, that I can't get, like in the original parabola, it's a function, but for the same y value, I got 2 different x's that went to it, which is okay for being a function, but when you do the inverse, then that makes the inverse not a function. So here's what I want to show you. If I'm looking at, say, the graph of the tangent line, it's a function. But I want you to see what's going to happen when we switch the x's and the y's, and that makes the graph rotate. Basically, it's going to rotate about 90 degrees whenever you look at an inverse. So looking at the sine, okay, they're showing you this is the inverse sine. Now, can you figure out why, if this is what the sine looks like? What happens if you switch this so that you end up putting these radian measures on the y-axis and you put what your outcomes are on the x-axis? Instead of being something that does this, won't it be a wave that goes this way? And then what's the problem? It's not going to cross or it's not going to pass the vertical line test. It's not going to be a function. So in order for your inverse to be a function, here's what we do on our trig ratios. We have to restrict the domain. In other words, we only want to take a section of it that will be a function. All right, and that means we're going to restrict ourselves to usually 2 quadrants to get a full cycle. So look at this again. All right. I have every possible outcome that we could get for sine between -1 and +1. And I'm getting those between -90 and +90. So I've got quadrant 1 and quadrant 4. I've got to pick the 2 quadrants. It'll be quadrant 1 and it'll either be 1 and 2 or it's going to be 1 and 4 to give back all of the possible values where it would be continuous and still be a function. Same thing with cosine. The only change is in order to get all these values to come out, we're not in quadrants 1 and 4 like we were in sine. We're in which quadrants? 1 and 2, going from 0 to pi. And in tangent, think about it this way. Whenever I turn this, it's going to mean I still have this same basic shape, but now these series of lines are going this way. All right? So to get the correct values I need for tangent, I'm going to choose between a -1/2 pi and a +1/2 pi. So it's going to be part, I'm going to go with quadrant 1 and quadrant 4 and just take one complete cycle in that inverse graph. All right. Now, I don't expect you to feel like, ooh, I've got this mastered. What I'm trying to do is just kind of give you a little visual to hang your hat on as we start to work in 6.3. And then when we get to those inverse functions, we'll come back and review this a little more. But you can see this web address up here. If you want me to make the link available in our course, I can. If you want to go in and play a little bit more with some of the trig things, because there are some pretty cool things in here, honestly. Okay, so far so good?
Mm-hmm.
All right then, let's go back to our notes. Okay, so we call these trig ratios, the graphs of these trig ratios, periodic functions. Alrighty, we're having a little communication problem. I was trying to zoom in. I guess I'll have to wait a second and try again. And so a periodic function simply means that whatever the function is, if I add an additional amount, the graph will repeat itself. So think about that sine curve. What did we say it takes to get one full cycle? If it's the original, just y equals the sine of angle x. In radians, that's how much to get one full cycle. 2 pi. So this is simply saying that for any real number x in the domain of f, every integer n and some positive number p. So we're going to make sure that n is an integer value, p is going to be a positive number, and if we wanted to multiply those together, okay, then we're going to find the least possible positive value of p to be the period of the function. If I want more than one period, it means I'm going to have to add n times whatever that value is to give me one period to it, and I could do that, okay? It's really irritating me that I can't zoom in. All right, so the circumference of a unit circle, we said, is 2 pi, right? The distance all the way around a circle is going to be 2 pi. So the least value of p for which sine and cosine functions repeat is 2 pi, because it has to take one complete trip around the circle to make that happen. There we go. Therefore, the sine and cosine functions are periodic functions with a period of what? What would be the period for sine? The period is how long it takes to get one complete cycle. 2 pi. We had 2 pi in every one of these blanks. Okay, so here's what this is saying. The sine of x would be equal to the sine of, and then in the parentheses we would have x plus, and then I don't know why that's a g, make that a dot. It would be any number times 2 pi. If we wanted to make the angle measure, this is basically saying if I wanted it to be the 2 pi plus, and then let's multiply n times, let's make n 3. We could do 3 times 2 pi and then add it to whatever this is. So in other words, it's just saying as long as you're adding some multiple of 2 pi, you're just increasing how many periods you're going to have in there. And the cosine of x would be equal to the cosine of x plus n times 2 pi if you want to have multiple periods in there. Now, if we just look at the standard 1 period for a basic function, if we're talking about the graph of the sine function, as the angle measure increases from 0 to pi over 2, then the sine will increase from what? Sine starts at? Hollow, right? So it starts at 0, and when you get up to pi over 2, what's that value you're at? Exactly. Think hollow. So it goes from 0 to 1 because we're going from 0 to a high value, okay? And then, let's finish this column, then we'll talk about cosine. Then, when we are going from pi over 2 to pi, so we're in the second quadrant, right? We start at the high value, which is 1, and we end up where when we're back at pi? 0. Okay, so visually, are you guys following? We're going from the axis, we go up, we go back to the axis. Then, when we're in which quadrant would this be? This was quadrant 1. This is quadrant 2. This is quadrant what? 3. When we're at pi, the sine ratio is 0. It's wherever we left off here. And we will end up going to what? -1, because we're going down to the low value. And then in quadrant 4, we go from back to 0. Okay, so this is just kind of filling in these key points. With cosine, what is it we're supposed to remember? Hollow, which means in quadrant 1, we decrease from what? 1 to 0. Okay, so we start here and then we come back to the axis. Quadrant 2, we go from 0 to axis down to the low. Quadrant 3, we go from to 0. And then quadrant 4 is back to 1. Okay, so that's just kind of, notice we keep coming back. We're going to re-summarize over and over until it sort of sticks. Some of us have different sticking points, I'll put it that way. Now, sometimes repetition's a good thing, right? Same thing we just did, except now this thing is including some additional angles. We're putting in some of those special right angles that we would encounter between, say, 0 and pi over 2. So let's see if you can figure out what those would be. If you need to, you draw yourself a special right triangle. I think that's always an excellent idea. So if this was 60, we could do one where we had a 30 degree, and then we could also do one with a 45. Okay, so let's go through and see if we can label these ratios. If this is 30 and this is 60, tell me how long this side would be right here. Let me zoom in a little bit more. Across from the 60 is what ratio? Or what would be the measure we use?
Thinking pi.
Oh my goodness, my goodness. Okay, I square root of 3. Across from the 30-degree angle is 1. And then this is 2 for the hypotenuse. Now, if my 60-degree angle is here, that means my 30-degree is here. So how long would this side length be? 1. This one would be, and this one is 2. And on a 45, 45, 90, how long are your legs? 1, 1, square root of 2. All right, so far are we okay? Now, I wrote it using degrees. This is written in radians. I can either think in radians over here, or I can take my degrees and I can change these to radians so that I will make sure I get these labeled right. Pi is how many degrees? 180. And what's 180 divided by 6? 30. So pi over 6 is the same as 30 degrees. What do you think pi over 4 is? 45. And pi over 3 would be 60. There you go. There's my pi over 2. And then how much would 3 pi over 2 be? That's 270. These are just axis angles down here. So it's only first quadrant angles that they've added into what we already knew. So since we're talking about sine, the sine of 0 is what ratio? 0. Remember, you start off with a hala. So it starts at the axis, it starts at 0. Now, when I'm at 30 degrees, or pi over 6 radians, what's the sine ratio? 30-degree angle, sine is how much? First of all, what's the ratio for sine? Opposite over hypotenuse. Look at your triangle. If this is 30 degrees, what's opposite over hypotenuse? 1/2. Are we together on this? I know we had a weekend. It's Monday. No, it's not Monday. It's Tuesday, but it still feels like a Monday. But you let me know if I've lost you somewhere. Okay, 45-degree angle. Looking at this triangle, what's going to be my sine ratio? That's right, 1 over square root of 2, which will be rationalized as square root of 2 over 2. Okay, now give me the sine ratio on a 60-degree angle. Look at your triangles carefully. Square root of 3 over 2. Now, I'm back at my axis angles. Pi over 2 is 90. What is the sine ratio for 90? Excellent. I'm back at a hala. So it's a high point, so that's 1. Pi is 0. 3 pi over 2 is, and 2 pi is, okay. Does that make sense? You make sure that you can find these. Now, you can use your unit circle diagram if you want. I just feel like it's easier if you've got this in your toolkit. I'd rather sketch this out and come up with it than have to pull out that chart and look at it. Now, talk to me about domain. Remember, domain would be all of the possible angle values that I could take the sine of. Do I have any kind of restriction on what my angles are? Can I take the sine of anything if it's an angle measure? Absolutely. So guess what the domain is? Negative infinity to positive infinity. Doesn't matter if I'm working in degrees or I'm working in radians. I have no restriction on what the domain can be. Now, what about the range? That's going to be the output. Yeah.
It's like a specific shape, like a triangle has a certain amount of degrees inside the triangle.
Well, here's the thing. Even if it's an obtuse angle, like 135 degrees, I can see where 135 degrees would be on the coordinate plane, and then the reference triangle that goes with that, my sine function is still going to be the same as whatever the reference angle is. You know what I'm saying? So I'm not restricted, because if this is 135 degrees, that would tell me this is a 45-degree angle. And so then I would just have to keep up with the SIGNS in quadrant 2, but I could still get the ratio that goes with this triangle. So I'm not really restricted on any angle measure. It's just going to tell me how many revolutions I might be making until I find my landing place on the coordinate plane. Okay, so does that make sense? No restrictions on X, but what are the restrictions on my output? When I have any angle and I take the sine of it, I'm always going to get a value between what? That's right. So how do you write that in interval form, interval notation? You do, because I'm going to go from -1 to +1. Remember, interval notation just tells me here's the starting point, here's the ending point, and when I want to include a value, I use a bracket. If I don't want to include a value, I use a parentheses. And so we had to have the parentheses on negative infinity and positive infinity because those aren't numbers, those are just concepts, right? Now, talk to me about what you think this graph is, what you see here. Is it continuous everywhere? We don't have any gaps, do we? We don't have any asymptotes. So it is continuous over its entire domain, which is negative infinity to positive infinity. Now, the x-intercepts, the places where it's crossing the x-axis, have x values in what form? And if you look, we've got pi over 2, pi, oh, I'm sorry, it's not crossing at pi over 2. It's crossing at pi, it's crossing at 2 pi, it's crossing at negative pi, it's crossing at negative 2 pi. Wouldn't you say that's just something times pi? It might be a positive number, it might be a negative number, but it's an integer. That's going to be for our basic sine graph. Those are where the x values show up in intervals of pi. And the period, you guys have told me multiple times, is, how long does it take to get one cycle? 2 pi. And would you say we have any symmetry with this graph? Now, if I've got symmetry, it means if it's a folding symmetry, those occur with the x-axis and with the y-axis. So if I fold on the x-axis and the halves match, I've got symmetry with respect to the x-axis. Do you think that happens here? No, because if I try folding on the x-axis, I've got this part that's going to flip down and it's not going to land on anything down here. Do I have any symmetry with respect to the y-axis?
No.
No, because it's going to end up reversing across itself. So the other kind of symmetry that I might have, there's 3 types typically we talk about, would be symmetry with respect to the origin. Okay, in other words, when you've got an odd function, it is symmetric with respect to the origin. And it means, basically, if I stuck a pin in it right here, and I spin this thing 180 degrees, it would look the same. Kind of like if you think about those pinwheels, if you blow on them, it doesn't matter where it lands, it always looks like what it looked like when it started. So look at this thing. If I were to stick a pin in it at 0 and I rotate 180 degrees, what's in quadrant 1 will end up down in quadrant 3. What's in quadrant 2 will end up over in quadrant 4. Is this thing going to look identical? It is. So it is symmetric to the origin, which means it is an odd function. And by the way, there are functions that are neither even nor odd. We're just checking for symmetry. And so that's what we would look for. If it is an even function, it's symmetric to the y-axis. If it's an odd function, it is symmetric to the origin. And for all values of x in my domain, it simply means if I were to replace my angle measure with the negative of that angle measure, it would make the output negative. So in other words, think about it this way. All right. Let's say we wanted to know what the sine of negative pi is. Well, what's the sine of pi? Oh, actually, that's not a good one. Let's don't pick pi. Let's pick pi over 2. Okay. So the sine of pi over 2 is 1. This is saying that if I did the sine of negative pi over 2, it ought to equal negative 1. Let's check it. If I look up here at my graph, here is negative pi over 2. Is the output negative 1? Yes. So if it's symmetric about the origin, when you change the sign of the x, it changes the sign of the y. All right? That's basically what it's saying. So that's a review from college algebra. Now, the sine function is related to the unit circle in that its domain consists of real numbers that correspond to angle measures or arc lengths. Because remember, the arc, when we're in radians, the arc length is the same as the central angle. And the range corresponds to the y coordinates or the sine values that are on the unit circle. All right, so at this point, we've just kind of defined, summarized things we know about the sine curve. So far, so good? Let's do the same for the cosine. So the only difference here is now we have been shifted, the sine function has been shifted or translated how many units to the left? Instead of it crossing at the origin, it now is crossing the x-axis where? What's this x value? All right, so it's shifted pi over 2 units to the left. It's the sine curve scooted over to the left is basically what we have, okay? Now, since we know cosine is a hala, let's go ahead and get these axis measures on here. So it's, oh, I'm sorry, hala, thank you. Okay, so since cosine is hala, we start when x is 0. What was the output? 1. The cosine is 1. If we're at pi over 2, the output is 0. The cosine of 90 degrees, or the cosine of pi over 2, we're back at the axis, so that's 0. What's the cosine of pi? -1, because that was 0, 90, 180, 270, and 360. If we're looking at it in degrees, this is what it looks like in radians. 3 pi over 2, we're back at the axis, so that's 0, and 2 pi, we end on a high note, right? Now, as far as these, I'm going to flip back to the triangles we drew a minute ago. Remember, we're looking for 30, and then 45, and then 60. So on the 30-degree angle, what is the cosine? Square root of 3 over 2. All right, so if you're looking at your triangles, what is the cosine of 45, or pi over 4? Square root of 2 over 2. And what would be the cosine of 60? 1/2. All right, does that make sense? We're just saving a little time since we did the work a minute ago on sine. Talk to me about domain and range, okay? Do I have any restrictions on what my angle can be in cosine? No, so it's negative infinity to positive infinity. What do I know about the range? When I take the cosine of any angle, I got to get a number between what and what? That's right, so it's the same range as we had on sine. It's a closed interval from -1 to +1. Is this thing continuous everywhere? Yes, it is. It's continuous over its entire domain, which is from negative infinity to positive infinity. Now, tell me where the x-intercepts show up on the cosine function. We said they were multiples of pi for sine. What do you think we're going to have here? It crosses at pi over 2 and 3 pi over 2 and -3 pi over 2. This one's a little sneakier to figure out how to write it as a multiple, so let me just give it to you. You're not going to have to do this on a test, by the way. But if we pick some number for n, multiply times 2 and add 1, and then that means for sure we've got an odd number. Wouldn't you agree? Mm-hmm. If you multiply that times pi over 2, then you will always have an odd multiple. That's the problem. What if we didn't have 2n plus 1? If we just had n plus 1, let's say we used 1 for n. 1 plus 1 is 2. Well, if I multiply 2 times pi over 2, I'm at pi. That's not right. So to make sure it's an odd number, that's why you want to do the 2n plus 1, okay, to keep that numerator where it's odd. Okay, the period is what? 2 pi. And let's talk about symmetry here. Do you think we have any kind of symmetry? This one is symmetric to the y-axis, isn't it? If I fold here, these halves would match exactly. So if it's symmetric to the y-axis, do you remember what kind of function that makes it? Excellent. It is an even function. So here's what that tells me. If I were to make my angle measure negative, so in other words, I know that the cosine of pi is -1. So what is the cosine of negative pi? Which is the same thing, isn't it? So when it's even, it means that if I change the sign on the angle measure, I still get back the same thing I would for the positive of that angle measure. Because if I fold on the y-axis, those points have to match up. They have the same y value. Okay? Now, here are some things that we're going to go over. Heads up. When you do graphing in my math lab, does it look anything like graphing on paper? No. Therefore, when we go through this section, you're going to want to make sure you practice graphing on paper, so you're going to be equipped to do this when you take the test. So what we do in the notes, you might want to make a point, even though you may be picking some graph in the computer on the homework, make sure you know how to actually put it on paper yourself. So this is going to discuss tools we need for graphing, and in 6.3 we're going to talk about two parts, amplitude and period. And if you remember anything about college algebra, in fact I'm getting ready to teach this in the next class today, we talk about transformations to basic functions, okay? And amplitude is the same thing as a vertical stretch or a vertical shrink. You know how we talked about y equals x squared earlier? Okay. Do you remember if I were to compare that to y equals 3x squared, what does this 3 do to my graph?
So it moves it up.
Good guess. I want to show you, okay?
I forgot.
It's all right. Let me show you in the calculator, okay? Because the parabola is something that's kind of familiar, so I think it helps if we look at it this way. So let me clear this out.
Oh yeah, the second number was the vertical, and the first one was.
So let's do it this way. We'll do x squared as the original. And then I'm going to make this one bold. And we'll see what happens if we make that a 3x squared. And I want to graph them at the same time. So there's the original. Here comes the bold. What did it do? Made it more narrow. It's called a vertical stretch. Do you know what happens if this number, instead of being 3, had been 1/3? It would make it wider. We call it a vertical shrink, which is really kind of weird when you think about it, but I think about it like a trash compactor. If you start mashing down this way, then this stuff have to go somewhere, it's going to spread out. Okay? So that is something that is applicable to trig functions, just like it was any other kind of function you might have looked at in algebra. If we see a number in front of the function, it's the very first thing you see after the equal sign, that's going to be a vertical stretch or a vertical shrink. Now, the number itself, just like it was on the parabola, will tell us which one it's going to do. What would you expect this to do if it's 1/2? A vertical shrink, which means that it does what? Yeah, it's going to squish it down this way. So here's what I want to show you. If we were to put the original graph, y equals sine of x, on here, and I'm going to do it on the paper, even though we can see it in the calculator, simply because we need the practice to make sure we know how to get this on. Tell me what goes on my x-axis. If I'm graphing y equals sine of x, what goes on my x-axis? These are what? It's my angle. Okay, so I've got to mark off units for my angle, because if I'm looking at this, I'm taking the sine of some angle. Now, it didn't say whether you had to use radians or degrees, but since we're trying to get more comfortable with radians, let's stick with that. So tell me, since that's 0, I'm going to mark off some units here, and I'm going to mark them off both on the positive and the negative end. Let's just stick with those axis angles. Let's don't make it any harder than we have to. Since it's sine, I'm going to think what when I graph? A holla. So if I go to 0, where is 90 in radians? That's what? Equivalent to, well, let's do it this way. Yeah, the whole, if I go a whole circle, that's 2 pi, right? So this would be negative 2 pi. What would have to be halfway in between 0 and 2 pi? Halfway is just, if I divide 2 pi by 2, I get pi. So that's pi, and that's negative pi. Is this making sense as far as trying to get it done? Okay, and then what would be halfway between 0 and pi? Pi over 2. So this will be pi over 2. This would be negative pi over 2. And that would mean this one is 3 pi over 2. Very good. 2 pi is the same as 4 pi over 2. And that's 2 pi over 2. So 3 pi over 2 would be right in between. And I've got them labeled for both the positive and the negative end of the axis. Are we good on that? That's actually going to be a real helpful skill a little bit later if we can get comfortable with that. Now, you guys told me my range was limited between what numbers? -1 and +1. So if I'm sketching the original graph, okay, it starts at the axis right here. When I get to pi over 2, what is my sine ratio? Well, it started at 0, so if I put in pi over 2, I'm at 1, because that's a high value. Back at pi, I'm at the axis, so that's 0. What about at 3 pi over 2? -1. 2 pi is 0. Now, if I sketch this, I have one complete period that goes from 0 to 2 pi, but I'm wanting to go this way. Can you help continue the curve? Remember what we said on this one, it was an odd function. So whatever the output was here, I need the negative of it over here. So at negative pi over 2, I should be where? At -1. Then I go back to the axis, to 0, and then I'll go up to +1 and back to the axis. And this should be a continuous curve. All right, now that's the original. What was it that we were asked to graph? 1/2 sine x. And I had mentioned to you that that 1/2 in front is either going to be a vertical stretch or a vertical shrink. So that's going to impact how high above the axis I'm going to go when I graph this thing. I was looking for a different color pen. I thought I had one in here, but I don't seem to find it. Let me double check, see if I dropped it in here. Do you? If you don't mind, let me borrow it, because I think it helps if we can kind of see how it compares. So basically, think about it this way. If I were to make this table, okay, where I had my 0, 1, 0, -1, 0, and that was when it was just the sine of x. If I multiply all these outputs by 1/2, I'm going to have what? 0, but instead of going up to 1, I'm only going to go where? To 1/2. And then that'll be 0, and this will go down to -1/2 and back to 0. So all I have to do is this. Hence the vertical shrink. Does that make sense? Okay? So that gives us the ability to kind of look at these simultaneously. So you can think of the graph of y equals some number in front times the sine of x as either a vertical stretch or a vertical shrink when, or actually let's do it this way. It's a vertical stretch when the number in front of sine is what? It'll stretch when it's what? When it's greater than 1. Okay, that didn't necessarily have to be a whole number. If it had been 3/2, it would have gone all the way up to 1.5 or to 3/2. Okay, so as long as it's a number that's greater than 1, you've got a vertical stretch. What do you think that vertical shrink would be? It's got to be a number between 0 and 1. Now, if it ends up having a negative sign with it, that actually means something else. If you remember from algebra, when we talked about transformations, a negative sign is a reflection over the x-axis. So that's going to actually be something different. We're only looking at what the number itself is. And this is called amplitude when we're talking about graphing trig functions. So if we are discussing amplitude, it has to do with how tall the graph is, if it's been stretched or if it's been shrunk. And that simply means this number that shows up in front of the function will give you the amplitude. If there's not a number there, it's going to go up to what? 1, and it would go down to -1. In other words, that number is going to tell you how many units above and how many units below the axis you're going to be.
So the first graph would have more
It would have more amplitude than that one because it does go up higher. It has a greater amplitude. Yeah. Now, in general, the graph of a function in this form, y equals sine, and now notice we've got a new letter. It's a b, and it's not in front of the sine, it's in front of what? It's in front of the x. It's not going to change the amplitude, it's going to change what the angle measure is, right? And what that does is it's going to change the period. All right? In other words, where 2 pi is 1 complete period, if we're just talking about the sine of x, then this is going to have a period that's different if I see a number that's in front of the x, and it will be different from 2 pi as long as that's some number other than 1. And we're going to have to pick up there next time. So